Step 14 is all about graphing and analyzing key characteristics of polynomial functions. In fact, this is our first step in Unit 4 that's all about polynomials. There's going to be a lot of vocabulary in this step, a lot of new terms. Fortunately, many of these terms are very simple concepts, but please try to pace yourself so you don't get overwhelmed with some of these new terms and concepts. We're going to first focus on some of these key characteristics, and then we will focus on how we can apply them to successfully graph a polynomial function. So the first 4 things I actually want to talk about together: relation versus function, and domain and range. It's important to kind of know what all of these are because they affect one another. In fact, a relation can be a function if every element of the domain is paired with exactly one element in the range. Now, if you don't remember what domain and range are, that's not going to make much sense. Let's step down and talk about domain and range. The domain, if you recall, is the set of all x values, and the range is going to be the set of all y value. So if we look at these examples here, let's try to find the domain and the range. The domain, all the possible x values. Again, it sometimes helps to start with your highlighter. We're looking just at the x values, which is the x-axis. I'm going to highlight whenever there is graph above or below my pen. And as you can see, it goes on forever. It looks like it kind of stops here, but remember there's an arrow, so it goes forever because of these arrows, which means that my domain is all real numbers from negative infinity to positive infinity. Let's take a look then at our range. The range, again, is the possible y values. So hopefully, for many of you, you're hearing all of this and thinking, yeah, this sounds real familiar. I remember this. We're going to start at the bottom. We're only looking at the y values now. Starting at the bottom, I'm going to highlight whenever there is graph to the left or the right. And there's still graph on the left and the right, all the way up until about here. Now, I know it's very difficult to specifically see what this point is. It's a little bit above 2. And for the point of this example, we're just going to estimate. So we know that we started at negative infinity, and remember, these arrows mean it goes down forever. And we got up to about 2.3. Now, it includes 2.3, so we put a hard bracket there. But notice, after this, there is no graph to the left or the right, so that is my range. Let's take a look at this other example. The domain, again, I'm going to look at my x values. It looks like it starts here and goes to about here, but remember, this arrow goes on forever, and it's going more and more and more left as it goes higher and higher. So that would go forever in both directions. So my domain, again, is from negative infinity to positive infinity. In my range, looking at my y values now, starting at the bottom, this arrow goes down forever. There's graph on the left and the right. As I move up, I still have graph on both sides. There's still graph to the left, all the way up. So the range in this example would be from negative infinity to positive infinity. So again, going back to talking about what makes one of these a function is if for every x value it's paired with exactly one y value. In other words, right here in this second example, my x value is 1, but my y value is either positive 2 or negative 3. There are 2 y values for this x value, which means this one is not a function. But right here, this one is a function. In fact, Often we use what's called the vertical line test to determine if something is a function. If you can pass a vertical line all the way across your graph, in fact, I'll draw one. Here's my vertical line. I don't know if it'll let me grab it or not. Let me try. There we go. Got my entire line graph. And now I drag it across. As I pass this line across the graph, it only touches the graph one time. Therefore, that is a function. Over here, it passes twice, 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 so that is not a function. Let's talk about one-to-one and onto. A function is said to be one-to-one if each element of the domain pairs to one element of the range. An function is said to be onto if each element of the range corresponds to an element of the domain. Now this gets very tricky. This is kind of a heavy concept to have to think about. Not all functions are both, but some of them are. The way I like to think about this is that the domain is sheets of wallpaper and the range is the wall. If you take your wallpaper and put it onto the wall, it would cover the entire wall. If you just put a piece up, you haven't put the wallpaper onto the wall because there's still wall showing. So if there are extra pieces of the wall that don't have any of the wallpaper covering them, like right here, we have a C, that is not onto. However, notice right here, there's a little bit of overlap. Remember, I'm trying to think of my range as my wall and my domain as my wallpaper. 3 and 4 kind of overlapped part of the wall here. That means it's not one-to-one. The wallpaper has to be perfectly placed, covering all of the wall without any overlap for it to be both. Here's another way to think about it. If a function has no two ordered pairs with different first coordinate and the same second coordinate, then it's called one-to-one. So for example, right here, I don't have any arrows going to the same number. So this would be an example of a one-to-one function. On the right, however, both R and B go to the number 3. Now, this might seem similar to what we just talked about above when we were determining whether a relation was a function. And it's a very similar analogy, only now we're going to use a horizontal line test. So in our example here, this one is one-to-one because it passes the horizontal line test. This one is not one-to-one. Both of these are functions because they both pass the vertical line test, but it has to pass a horizontal line test to be one-to-one. In other words, if you plot both of these mappings, you would see that right here, 2 x values give you the same y value, which means it would fail the horizontal line test and it would not be one-to-one. Onto functions. For every element in the range, there is an x value. Notice right here, 4, 2, 5, they all are associated with x values. But over in this example, there's also 7 and 3, and they don't belong to anyone. When that happens, the function is said to not be onto. Let's look at an example. Let's first start by naming the domain and the range. Remember, the domain is all the x values, which in this case is -6, -5, -3, -1, and 6. The range is all the possible y values. We usually like to list them in order from least to greatest, as I did with my x values. -9, -7, -1, 7, and -9, we already have it on our list, so we don't have to write it again. There's our range. Now let's take a look at this and try to decide if this function is one-to-one onto, both, or neither. And again, I think it's very helpful to try to give it a rough sketch and see what happens. So -6, -1, -5, -9, -3, -7, -1, 7, 6, -9. Well, it looks like it's going to pass the vertical line test just fine. So it is a function. But the horizontal line test, right here, again, it's just a rough sketch, but it fails the horizontal line test, so it is not one-to-one. Now we need to think about, is it onto? This function is said to be onto if every element of the range pairs with an element from the domain. -9 pairs with -5, it also pairs with 6. -7 pairs with -3, -1 pairs with -6, and 7 pairs with -1. So this function is said to be onto. The next topic I'd like to talk about is discrete versus continuous. This is a very simple concept. Discrete just means that the set of points in our relation they aren't connected. They're distinct. Sometimes you'll see this example in a lot of real-world problems where you can't have something that's continuous. You know, if you're talking about number of visits to a store, you can't visit a store 2.7 times. You can visit it 2 times, or you can visit it 3 times, but not in between. Other times, you can have your scenario be a very continuous relation, like in graph B. Often we're talking about time versus temperature. Temperature is continuous. The temperature can be 32.8 degrees outside. That's an example of where it would be continuous. End behavior. When we're talking about the end behavior, we're just looking at the behavior of a graph as we go all the way to the right or all the way to the left, as x approaches positive infinity or as x approaches negative infinity. The hardest part about end behavior is mastering the notation. This is how we're going to write it. Notice that every graph will have a right side and a left side. The right side we represent as x approaches infinity, but we don't want to write out the word approaches, so we just draw an arrow. For the left side, we're going to write as x approaches, you got it, negative infinity. And now we need to explain what y does as we go to the right. So if I start in the middle of my graph and move to the right, tracing all the way to the right, as I go to the right, I'm going down. Remember, infinity is up, negative infinity is down. Infinity is to the right, negative infinity is to the left. So as I move to the right, that's what this literally means right here, moving to the right, my y value, or my f of x value, approaches negative infinity. Let's go the other direction. As x approaches negative infinity, in other words, as I move to the left on my graph is going down to negative infinity. So y is going down to negative infinity. Now, sometimes you will see these flipped around. It's just a notation thing. Sometimes the problem will say f of x approaches negative infinity as x approaches infinity. That means the same thing, kind of like if you say the sentence, as I read a book, I get sleepy. You could also say, I get sleepy as I read a book. It means the same thing. The as portion always accompanies the x, and then f of x stands on its own. Let's try to find the end behavior of this second example. Again, we're going to have x going to the right, and we're going to have the other end going to the left. And we need to explain what f of x does for each of these. So, as x approaches positive infinity, going to the right, y goes down to negative infinity. And then as x approaches negative infinity and goes to the left, my y values are going up, getting bigger and bigger and bigger to positive infinity. A couple of things to notice here. We don't know the equations or the polynomials that represent these two graphs. We're going to learn more things this step that will help us deduce what that polynomial equation could be. But polynomials can have an even degree or an odd degree, meaning the highest degree or the highest exponent can either be even or odd. For example, if the degree is even, like y equals x squared, you guys should be very familiar with y equals x squared from Unit 3. Notice as x goes to the right, it goes up. As x goes to the left, it goes up. And again, this is an example of where the notation has switched around, okay? As x approaches negative infinity and goes to the left, y goes up. As x approaches positive infinity and goes to the right, y goes positive. When both y values match, they're either both going up or they're both going down. These functions are said to be even degree. When one side goes up while the other goes down, like in these examples, these are said to be odd degree functions. So right away, looking back at our first two examples, we don't know what the degree is, but we know this one is even and this one is odd. A way I like to imagine that is to think about working out with a set of dumbbells. If you put both dumbbells over your head, or if you curl both at the same time, or if you have both hanging down on the side at the same time, you feel very balanced and very even. But if you put one over your head and one down by your knee, it feels a little bit odd. So if one is going up while the other end is going down, that's considered an odd degree.